Hey students, I will explain the solution to this problem in this video. So first read the problem. Two geometrically similar pumps are running at the same speed of 1000 rpm. So first they said geometrically similar pumps running at the same speed. Both the pumps are having same speed. One has an impeller diameter of 0.4 meters. So and the discharge of 30 liter per second. So against a head of 20 meters. So it is working against a head of 20 meter, maybe the total head. The discharge delivering by this pump is 30 liters per second, and the diameter of the impeller is 0.4 meters. Okay, we don't know it is whether it is a internal diameter or external diameter. We just said the diameter of the impeller is 0.4 meters. So if the other pump, so for the second pump, if the other pump gives off of this discharge rate, so means here the discharge is 30 liter per second. So the second pump is giving 15 liter per second. 15 liter per second discharge. Determine the head and the diameter of the second pump. So for what head it can able to deliver this 15 liter per second discharge, and what will be the diameter required, diameter of the second pump. These two things we have to calculate. So first see the given data N1 N2 for two different pumps, pump 1 and pump 2. The speed is N1 equal to N2 1000 rpm. D1 for the pump 1 0.4 diameter of the impeller, that is 0.4 meters. Discharge 1 30 liter per second, that is 30 by 1000 0.03 meter cube per second. H1 is 20 meters. So Q2 is also set half of this 30 by 2 15 liter per second 0.015 meter per second. So here we have to find out head for the second pump H2, diameter for the second pump H2 and D2 we have to calculate. So how to do this? So first of all, here this is geometrically similar turbines. So we'll use the uh, the equations that we have that is available for the geometrically similar turbines. So for geometrically similar turbines, so first from the given data, see, so H2 D2 we have to calculate. So specific speed equation can use. So ns will be specific speed. Ns will be n root q by h power 3 by 4. H power 3 by 4. So this is the specific speed equation. Speed of the pump, discharge of the pump, and head of the pump. Okay. So for geometrically similar pumps, this specific speed must be same. So if you give number for the pump 1, it will be N1 Q1 H1 power 3 by 4. For pump 2, N2 Q2 H2 power 3 by 4. So NS will be same for geometrically similar turbine. So this equation can be written N1 under root Q1 by H1 power 3 by 4, N2 under root Q2 by H2 power 3 by 4. So all the data is available with us. N1 is equal to N2, Q1 is known, Q2 is known, H1 is known, H2 have to calculate. So by solving this equation, okay, by rewriting, so you get this for H2, and by solving that equation, you can calculate H2 is 12.6 meters. So the second pump can be worked against a head of 12.6 meters, right? So similarly, we have the head coefficient equation for two pumps. That will be under root h manometer, under root h manometer means manometric head upon dn. Manometric head upon dn is a head coefficient. Head coefficient. So for the head coefficient will be constant for geometrically similar turbines. So same thing here written here. D is proportional to under root hn. So you can write like this. D is proportional to under root hn. So that means under root h1n1 is proportional. D1 is proportional to this, D2 is proportional to this. So we can say D1 by D2 is proportional to under root H1 by H2. because N1 uh, uh, and N2 are same, because N1 and N2 are same. So here d1 by d2 can be written as, because the constant of proportionality will be h1 by h2. So solving this, you can get this. Otherwise, you can simply just use this equation, under root h manometer h1 divided by d1 n1 is equal to the root h2 divided by d2 n2. So h1 is known, h2 is known, n1 is known, n2 is known. So d2 you have to find out, d1 is known. Just simply use this equation. You don't bother about which one is proportional to which. Just use head coefficient equation and solve this problem. You will get this answer. Okay, thank you.